As you'll be aware, colour blindness, or more accurately perhaps colour vision deficiency, is pretty common. You've probably seen these kind of colour vision test plates. So this is a cleverly designed one where, as it says here, if the computer display were correctly calibrated, then people with normal vision should see the number 74, but people who are colourblind may see 21, and those with total colour blindness may not see any numbers at all. So colour vision deficiency can be caused by missing a cone type altogether if you simply don't have the genes to make that type of cone. And they're given names reflecting the Greek for first, second and third, counting L, M, S. So somebody with protanopia, first not seeing, has got no L cones. And a retinal mosaic from such a person is shown here. So on the left we have the normal retinal mosaic with the L, M and S cones marked in red, green and blue respectively. But here's a protanopic retina, and you can see there are just the M and the S cones but no L cones at all. Somebody with deuteranopia, second not seeing, is lacking their M cones, and tritanopia is very rare, but you do come across it occasionally where somebody has no S cones. Now, a different form of colour blindness is where you're not lacking the cone type completely, but its spectral sensitivity isn't quite like the rest of the population. So the peak of the M cone sensitivity may not be at its usual position in terms of wavelength. And so, in the sense, your colour vision is as good as anyone else's, but you're just not going to agree with the rest of the population about what colours are. You may name them differently. Now, many of the genes involved in colour vision turn out to be on the X chromosome, and of course men only have one X chromosome, whereas women have two. And so that means males are more likely to have problems with their colour vision. Women have a kind of second chance, in that even if you're lacking a gene on one of your X chromosomes, you may have it on the other X chromosome, whereas men don't get that. And so around 8% of males have got some form of red-green colour blindness versus only 0.6% females, so about 10 times as many men as women have colour blindness. Interestingly, another consequence of this, the fact that genes involved in colour vision tend to be on the X chromosome, is that it's possible for women to have two different types of L cone, or indeed M cone. They can have the genes encoding an anomalous L cone on one chromosome, but a normal L cone on their other chromosome. And if those both end up being expressed in the retina, then these women can actually end up with 4 distinct classes of photoreceptor, of cone photoreceptor, and they're called tetrachromats. Now, it's not as cool as being a tetrachromat like that astrildid finch we saw earlier, because 3 of your cone classes are very close together in wavelength space. And it's very difficult to demonstrate that these women can actually use their 4 different cone types in order to perceive different forms of colour that the rest of us can't see. In other words, to discriminate spectra that look the same to us. So there would be things that would be metameric for a normal trichromat that a tetrachromat could tell the difference between. And my colleague Gabrielle Jordan here at Newcastle has done a lot of work on this, and she has actually identified just one woman who can clearly use her 4 different classes of cone photoreceptor in order to achieve this kind of colour vision superpower. She's a true tetrachromat. Now, I'm sure you remember the sinusoidal luminance grating. The L and M, I'll ignore S, cone stimulations rise and falls together so that their sum varies but their ratio doesn't. So you perceive the brightness of this grating rising and falling, the black and white bars, but you don't perceive any colour change in this achromatic luminance grating. But we can actually create chromatic gratings in a very similar way. So here, this won't be working on this uncalibrated screen, but if this were correctly calibrated, what it's trying to do is produce a situation where the total L plus M stimulation is exactly the same across this whole grating, and it's only the ratios that are changing. So we're going from regions where L is activated and M isn't, to regions where M is activated and L isn't, but the total is meant to be staying the same all the way across this grating. And similarly, you can construct a blue-yellow chromatic grating. So here the idea is that, again, the total luminance, so effectively just L and M, is staying the same, and only the S-cone excitation is varying across the stimulus. So we had the luminous contrast sensitivity function, and you'll remember that you can kind of eyeball your own contrast sensitivity function based on how high these stripes are visible in this picture. And we can do a very similar thing for chromatic contrast. So this is just the same structure as the previous image, but now we're varying colour rather than luminance. And you'll notice something interesting, I hope. Once again, you should see that the stripes go up less far on the right, so there's this high frequency fall off in sensitivity, but there isn't really a fall off on the left. If I were to ask you to draw on where you can see the stripes, you might draw something like this. So there's very little fall off at low frequencies. So whereas the luminance contrast sensitivity is bandpass, so we're most sensitive at these middle spatial frequencies and relatively insensitive to brightness variations on very coarse scales, actually with the chromatic contrast sensitivity function, we remain sensitive to colour variations even at very coarse spatial scales, and we're pretty insensitive to colour variations on fine spatial scales. So one immediate consequence of that is if you want somebody to see fine details like text, then make sure that has luminance contrast. Don't just convey that information via colour. One application of our low resolution for colour information is actually how to transmit your television signal. So when television or video information is broadcast or streamed over the internet, generally the colour information is sent with much worse resolution than the luminance information, and that's what this set of images here is trying to demonstrate. So the luminance resolution, a black and white image, is being sent with high resolution, very detailed pixels in all four images, but the colour information is only transmitted very coarsely here on the left, and then as you move to the right, the colour information is transmitted with more and more detail. And then the information is overlaid, so that coarse colour information is overlaid on the fine luminance details. And the point to take away here is that actually these images look very similar quality. If you look closely, you may be able to convince yourself that there's some problem at the colour boundaries here, but certainly at initial glance you don't notice that there's a difference. And that's because of our poor sensitivity to the fine details of colour. And so television engineers are able to sneakily save themselves some bandwidth in that way by not broadcasting colour information at unnecessarily high resolution that the viewer isn't going to be able to appreciate anyway. Here's a nice demo of how colour adopts luminance boundaries in this way. Your visual system knows you're not very sensitive to the fine details of colour, and therefore if you put on a crude colour wash, we tend to perceive it as locked to the nearest luminance boundary. And you can see that here. So if you look at this, hopefully you see green stars on a pink background on the left and pink stars on a green background on the right. Or you might see green stars and pink kind of octagons versus green octagons and pink stars. So on the left there appears to be much more pink because the octagons take up a lot more area than the stars, and on the right there appears to be a lot more green. Would you agree with that? Okay, but in fact the colour information is exactly the same in these two images, and the only thing that's changing are the luminance boundaries. So here's zooming in on each of these two images, and hopefully it looks much more obvious that the colour is exactly the same in the two, and the only thing that's changed is where you draw these boundaries on. And we have the tendency on the left to perceive everything inside the star as being a more or less uniform green, and everything inside this octagon as a more or less uniform pink, even though you can see it's clearly not uniform. And conversely, when you put the luminance boundaries, these black lines, in a different position, then there's this tendency to perceive the octagon now as being filled up with a uniform green. And since the octagon's bigger, that means overall the image looks much greener here on the right. But in fact, there's no difference in the colour channel, and that's just an illusion created by your tendency, your brain's tendency to lock colour information to luminance boundaries like this. Now, a related consequence of our sensitivity to colour variations on coarse scale and our insensitivity on fine scale is the different circumstances under which we get colour contrast versus colour assimilation. So to talk through what I mean by that, look at these coloured patches on this background. I hope you'll agree that this one here is grey. Now, I've surrounded the patches in the bottom with a green background. And I don't know about you, but now this grey patch here, which is in fact exactly the same colour as you can verify on your computer screen, it now looks distinctly pinkish to me. And that's an example of colour contrast. The grey patch looks more pink in contrast to the green background. So that makes sense, and I think it makes sense from an ecological point of view, because one interpretation of this scene is that a green filter has been placed, a green piece of perspex or something has been placed over the bottom part of this scene, in which case if this is going to appear grey on our retina, the object in question must actually be pink, and so it makes sense for us to perceive it in that way, since, as we were stressing earlier in the course, the visual system is interested not in what's falling on your retina but what things are made of. Here's an example of grey surrounded by green, and now we have the opposite effect. So what's going on here, these little grey squares are the same shade of grey on both sides of the image, but here, I hope you'll agree, the grey looks kind of greenish, and here it looks pinkish. So that's just the opposite of what we were discussing. Even though it's surrounded by green, the grey now looks greenish rather than pink in contrast. And that's colour assimilation. And the distinction between the two of them is really one of scale. So at fine scales we get colour assimilation, and at coarse scales we get colour contrast. And that's thought to reflect the relatively little information that we have about colour at fine scales.